We'll proceed with constraint, extreme point, constraint minima and maxima. So whatever we are seeing, where we have been seeing, that is unconstrained minima and maxima. What is constrained minima and maxima? Constrained minima and maxima means we have some condition. Based upon the condition, we will calculate the maxima or minimum. So that is the scenario. What is constrained? What is unconstrained? Means if I have constrained, unconstrained. If I have a plane, if I have a plane and plane is throughout x-axis and plane is throughout y-axis, full full x-axis, full y-axis. We are talking about 3D, where there are two independent variables, that is x and y. X along full x-axis, y along full y-axis. Now, in that we may find many local minimum, local maximum. Local minimum, local maximum means wherever I see this kind of curve or this kind of curve. Okay, either it is a hill or it is kind of a ditch. So if we kind of valley kind of, either it is a hill or it is a valley, so those are local minima or local maxima. Now among them, whichever is the highest, that is global maxima, and whichever is the lowest, that is the global minima. Now this is called unconstrained unconstrained minima and maxima, unconstrained extreme points. So that is the scenario, unconstrained extreme point. Now we'll talk about constrained extreme points. Constrained extreme points. So what is constrained? What is unconstrained? So I believe that we have talked about that is called closed region. We have closed region, we have bounded region, we have unbounded region. Closed region, bounded region, and unbounded region. Closed region means there is a region where is a kind of means closed region, as we have talked, we have a center, and from the center there is a radius k. If I have a center, then there is a radius k. With radius k I draw a circle, and that circle is a region. If that region is closed by a boundary line, then it is called closed region. If it is not closed by a boundary line, then it is bounded region. If this k is infinite in one direction, then it is unbounded. Okay, so closed region, bounded region, unbounded. So here now what is constrained extreme point? Unconstrained extreme point means that I have a kind of minus infinity to plus infinity, and minus infinity to plus infinity in x direction, minus infinity to plus infinity in y direction. In that case, whatever I find, I say this is global maxima and global minima. One global maxima, one global minima. Or so many bumps if I see, then those are local maxima. So many ditch I see, then those are local minima. So local minimas can be so many, local maximas can be so many, whereas global maxima is one, global minima is one in an unconstrained region. So that is the idea. Now we have a constrained region. Constrained region in the sense that I have a line, and below the line you have to find maxima or minima in a region. Constrained means in a region, in a closed region, probably. So in a closed region, now you have to find maxima minima, that is called constrained region. Constrained by a particular algebraic equation like x square plus y square equal to 2 square. X square plus y square equal to 2 square. Or rather, I would say x square plus y square less than equal to 2 square. Means region is A circle where radius is 2, including its boundary. Inside that circle, what is maxima or minima for any equation fx? So there are two equations, fx, gx, fx, gx. Fx is the main function through which we draw the graph, whereas gx is the constrained region. Fx is the actual graph and Gx is the constraint region. Earlier, Fx used to be the earlier graph and Gx used to be unconstrained region, not required. Minus infinity to plus infinity, x, y minus infinity to plus infinity. There you have to find the global maxima or minima. Now, Fx is there for which we have the graph. We have Gx, that is the closed region. Inside the closed region, if fx is drawn all over the xy plane, but when it is overlapping the gx region, inside that region, what is maximum? Global maximum. Global is a kind of a term that is inside a region. So if it is a constrained region, inside the constrained region, if I say x square plus y square less than equal to 2 square, then it is a constraint, circle is a constraint region including its boundary, that is the perimeter. Now if this is the circle, on xy plane and fx is fully drawn, then over the circle I have to take the xy including its boundary. That, only for those xy I have to consider the fxy, and then I have to find in that region what is maximum and what is minimum. This is constraint minima and maxima. Okay, so what can be formula for this? If I have fxy, then I can calculate dfxy dx, partial derivative along x-axis, dfx by dy, dfxy by dx, dfx by dy, and then I set both the partial derivative to 0, then I'll come to know set of xy points where the fxy is critical or extreme. It has extreme. So if those points are x1, y1, x2, y2, x3, y3, then I'll check if x1, y1, x2, y2, x3, y3 they fall on a constraint region or not. So idea is, if I have a constraint region gxy, gxy is a constraint region in xy plane and fxy is a full-fledged graph. Okay, wherever the intersection happens, fxy and gxy. So fxy for all the xy points that is in the gxy, for that what is the minima or maximum? That is the question. Not anyway, constrained to that closed region gxy. fxy has full value for the minus infinity to plus infinity as far as x is concerned, minus infinity to plus infinity as far as y is concerned, but only now I don't have to take all the xy, only xy that falls inside or on the boundary of the gxy. Okay, if that is the case, then what is maxima and what is minimum? Okay, now what I did, I calculated dfxy by dx, dfx by dy, and I set it to 0. I get a set of, it can be many points also, I'm not saying. Suppose I got 3 points, x1, y1, x2, y2, and x3, y3. At this point, I saw that it is extrema. Now I'll check if it falls in the closed region or not. If x2, y2 happens to fall in the closed region, then certainly the fxy has one minimum or one maximum that we saw that it is inside the gxy. So now later we'll check it is minima or maxima, but it is inside the gxy. So one minima or maxima we have found. But that now this is the one scenario. One scenario. Anyway, what we have got. Another is, now we have, if fx is crossing the gxy, then inside gxy I have found the kind of minima or maxima. Now fx, wherever it is touching the boundary of gxy, fxy when it is overlapping gxy at those points. At one point x2 y2 I saw that fx makes a local minimum, fx make a local minima or local maximum, fx makes a local extreme point. So one extreme point I have found now. Other can be at the boundaries. If inside that there is no extrema, then other can we have to check at the boundary. Wherever it is touching the boundary, at those points I have to check that which one is maximum, which is minimum, and anyway one I have found the extreme point. So all the extreme point, one is touching the boundary, and whatever falls inside it, all points now I have to take, then calculate fxy over all the points, and then I have to see which one is maxima and which one is minima. If I get it, then certainly I have found the global maxima, global minima as far for the gxy as far as for the fxy. For the fxy, what is global maxima, what is global minima as far as the constraint is gxy. Earlier, the constraint, if I say gxy was the constraint earlier also, then it was minus infinity to plus infinity, minus infinity to plus infinity. If this is x-axis and this is y. Now there is a constraint. Let's take a very famous example. Like if I have fxy, fxy equal to x to the power 2y3 into y to the power 1y3. Fxy equal to x to the power 2y3 and y to the power 1y3. So fxy is a graph, fxy is a function with two independent variables x and y, x to the power 2 by 3 and y to the power 1 by 3. The x, if x is varying, then it would vary by 2y, power 2 by 3. If y vary, then it will vary by 1 by 3. Both are multiplied to each other, that is fxy. Now I have to tell fxy as its maxima or minima. I am interested in maximum. Where fxy is maximum, where constraint is that x plus y should be less than equal to 3. Earlier, there was no constraint. Unconstrained region, I have to find maxima or minima. dz, if I say fxy is z, then dz by dx, dz by dy, two partial derivatives. Now equate it to 0 and try to come up with xy, set of xy, and then check at these x y. I have found the extrema, that is done. But check, please check, these are maximum or minimum. Now it is the constraint region where I have to find the constraint region is x plus y less than equal to 3. If y is 0, then x is less than equal to 3. If x is 0, then y is less than equal to 3. X plus y less than equal to 3. So this is a line that intercept x-axis and y-axis. X-axis at 3 and y at 3. If that is the case, so if this is x, this is y-axis, this is x-axis, this is y-axis, this is x-axis, this is origin. If that is the case, then this is 3 on x-axis and this is 3 on y-axis. Then line is like this. If this is x-axis, then 3 is 3 comma 0 and this is y-axis, then 0 comma 3. If I draw a line that is x plus y less than equal to 3. Less than equal to 3 means if this is the line, then this side of the line, that graph should fall. Above this, I am not interested. This is constrained extrema. Constrained extrema. So one situation is I'll try to find all the extrema that is below this line. If this is x plus y less than equal to 3, then this line on the left side, whatever region I am seeing there, the extrema, we get or do not get. If I am not able to find it anyway, then I have to find touching the x, touching the line, the constraint line, what are the points that fx touches those lines. On those lines, now I have to sort it and find out which is maxima or which is minima. We are interested in maxima. So which is maxima? And that I can say that within the constraint region x plus y less than equal to 3, that is a line, I found inside it somewhere, that is a maxima, or on the line I found somewhere. So Lagrange, I believe I am pronouncing correctly. So Lagrange is a mathematician. Now he worked on it. So now what he is saying is we have another version of whatever Lagrange has done the mathematics, certainly we don't support it. Okay? Because it is based upon his brain only. There is no logical proof or something like that much on it. Anyway, so we will see our proof also. But anyway, let's move ahead with whatever is available. So what he thought about it. Now, if I have fxy equal to x to the power 2 by 3 and y to the power 2 by 3, x to the power 2 by 3 and y to the power 2 by 3, that is fxy, then for a particular xy, if I say x0, y0, then particular xy, I have fixed f. If I have one xy, then f cannot be variable. It is fixed f value I am getting. But if f is fixed, then I would get set of x and y where it would result in a particular f because it is variation of x and y. So if x is less, then y will be more. Then it satisfies. If f equal to, suppose f equal to n, f equal to n, to satisfy the n, if I have x value to some, then I have y value. If I keep changing the x value, I can still get n if I change the y. So I would get a set of points in xy for which the fxy would be constant n. Okay, so fxy is nothing but vertical. We also call it, so we can draw contours. Contour means if vertical component is 1, 2, 3, 4, 5, 6, 7, 8. If vertical component is separate, as these vertical component, what is the set of xy that we are expecting? Okay, what is the set of xy that we are expecting a particular vertical value, that is z. Okay, now I can draw contour diagram. Now I have x plus y less than equal to 3 line. Now if f, now f I can keep constant and then see the variation in xy. I cannot keep xy constant, xy as constant and see variation is in f. These explanation also what we are giving as far as the existing solution is concerned. This explanation is also not available anywhere. Anyway, so now if I have xy fixed, for fixed xy, the f is dependent and f is not variable. Only one point I'll get. But if I have fixed f, that is contour height, then I'll get set of x and y. For each f, 1, 2, 3, for whatever, I draw a set of y. So set of y will result in a line. Understandable. So fxy is a function equal to x to the power 2 by 3 into y to the power 1 by 3. Now if I keep f constant, means vertical constant, or vertical cross section constant, or for a particular contour, then it would be satisfied by set of xy value. If it would be satisfied with set of xy value, then those xy in xy plane we will draw for a particular contour. Keep doing that. For contour fxy equal to 1, 2, 3, 4, 5, 6. Now check that where this contour intersect the constraint line, that is x plus y less than equal to 3, as tangent. This is what we want. As tangent, we are drawing graph of fxy. We are not drawing graph of from the xy perspective. There is a graph where xy is variable, then we see the f. Here means here the graph is not for x and y, graph is for contour, for the fxy, that is the z. For fixed fxy's, now we are drawing the graph. For a particular fxy, particular f, generally we see that it is touching the constraint line at some point. that is x0, y0. If it is touching that line x plus y constraint line at point x0, y0, then that line, the constraint line, is tangent to the fxy, for that where fxy is fixed. So for that particular contour, if I draw set of contours, fixed vertical, for a fixed vertical set of xy point if I draw, then if it is touching the constraint line, then at that point where it is touching, so if this is a constraint line and this is fxy equal to 2, I am drawing, and it is drawn for various x comma y points, and it is touching the constraint line and it is passing. If f equal to 3, then probably it will pass above it. F equal to 4, it will pass above it. F equal to 1, it is passed underneath it. That is also okay. But if I need maximum, right? Idea is what is the x and y for which f is maximum. I have to find maximum f for x and y, but x and y should fall inside or on the boundary of a constraint line, that is x plus y less than equal to 3. That is the query. Now, if I draw various fxy, okay, for f1, 2, 3, 4, 5, if f is completely inside the constraint, then anyway, it is satisfying what we need. But we want maximum f, right? So f we keep increasing, till it is touching the constraint line. If I increase again, it will be above the constraint line. If that is the true, then the place where it is touching the constraint line, that f value, that vertical value is the maximum value. I have to just find at what point it is touching the constraint line. If I say f equal to 2, at 2 it is touching the constraint line. If f is 1 or 1.9, it is below the constraint line. So that is not the maximum value. So maximum, it is understandable. If this is x-axis, this is y-axis. If this is x-axis, this is y-axis. This is the constraint line, x plus y less than equal to 3. Now, if I have set of xy point for a particular f, if f equal to 1, then I have an xy point, it is something like this, draw a line. So keep increasing the f, because now if I draw a set of xy for f equal to 1, it falls inside the x plus y less than equal to 3. So we like it, means it is below the constraint line, so it follows the constraint. But we want maximum f. So f we keep increasing, Now this is the line x plus y less than equal to 3. This is the line, and f is increasing. One time it will cross the line. This is what we don't want. We want maximum that it will touch the line. If it is touching the line, means the line is tangent at the point at which it is touching. This is Mr. Lagrange is saying, and he is saying correct. So it is touching the line. So f, if we start from very minimal value, then it will be inside the constraint line. If we keep increasing the f, because we want maximum f, right? If we keep increasing, one time will come when it will touch the line. If I increase it again, it will be above the line. So where it touches the line, that f I have to keep, and where the touches the line x0, y0, that is the extreme point that we are looking for. So the line that is touching the f, that is supposed to be tangent to the function. So gxy is x plus y less than equal to 3. Gxy is tangent to fxy for a particular value of f, that is the maximum f. Where it will happen is point x0, y0. If that is the case, then x0, y0. Now suppose that this is okay. So suppose that this is f, okay, or this is f. F is a kind of crescent. This is f, and this is the constraint line and f. So f is touching the constraint line at x0, y0. So that is a tangent. Now if I have a gradient vector of fxy, gradient vector at any point is perpendicular to the point. means it is radial. So if I have a tangent, if this is a curve, and at some particular point if I have a tangent, then gradient vector will be perpendicular to the tangent. This is what we have seen. Now if I have a constraint line, if I calculate gradient for this constraint line also, and at that point then again the gradient vector will be perpendicular. So gradient vector is perpendicular if it is a curve. If it is a curve, the point at which we are calculating the gradient vector, at that point it will be radial, means perpendicular to the curve. If it is a tangent, if it is a line, and then we are calculating the gradient vector from this line, again it will be perpendicular. So if I have fxy like this and gxy is constant line like this, then at this point they are touching each other. So the gradient vector of fxy is in this direction. Gradient vector of the constant line is also in this direction. They are parallel to each other. But vector, gradient vector, it is a vector which has a magnitude and a direction. Direction is same, that we came to know. Magnitude may differ. So I would say if gradient vector of fxy equal to gradient vector of gxy, because their direction is same. Gxy I will multiply with the lambda, lambda. So lambda is a Lagrange multiplier. This is what Mr. Lagrange calls. So fxy, so gradient of fxy equal to lambda into gradient of gxy. Fxy, gxy direction is same. That's why we are saying that gradient of fxy equal to gxy. But magnitude is different. So I multiply lambda in the gradient of gxy. Now they are same. So gradient of fxy equal to gradient of gxy into lambda. Okay, at point x0, y0 where they touch each other. So if this is fxy and at x0, y0 point it is touching the constraint line gxy, at this point fxy gradient vector perpendicular and gxy gradient vector, they are parallel to each other. So gradient of fxy equal to gradient of gxy into lambda to compensate the magnitude difference. Now, if I have fxy equal to x to the power 2 by 3, y to the power 1 by 3, then gradient vector fx, the first gradient fx, would be 2 by 3 into x to the power minus 1 by 3, y to the power 1 by 3. Whereas the fy is 1 by 3, x to the power 2 by 3, y to the power minus 2 by 3. Now here we have line equation as x plus y. So gradient vector is I plus j. So gradient vector for gxy is I plus j. Gradient vector of fxy is 2 by 3, 2 by 3 x to the power minus 1 by 3, y to the power 1 by 3. Where fxy equal to x to the power 2 by 3 into y to the power 1 by 3. So gradient of fxy is is 1 is 2 by 3 into x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3. This is gradient vector of f, and gradient vector of g is I plus j. So lambda into I plus j. So this gradient vector equal to lambda into I plus j. Okay. Now, if I see, then lambda I plus lambda j equal to 2 by 3 x to the power minus 1 by 3 plus 1 by I plus 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3 equal to lambda I plus lambda j. Now, lambda equal to, if I see, then lambda equal to x component and lambda equal to y component. Now, if I equate both sides, then we get like 2 by 3 x to the power minus 1 by 3 into y to the power 1 by 3 equal to 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3. Now, if that is the case, then Then if I take x here x is minus 1 by 3. If I take that side and there y is minus, I take this side, then it becomes 2 into y, 2 into y equal to x. Okay, so x equal to 2 into y, because 2 by 3, so and here 1 by 3, 3 gone, 2 to the 2 into x to the power minus 1 by 3 into y to the power 1 by 3 equal to x to the power 2 by 3 into y to the power minus 2 by 3. So x I take that side, y I keep this side. So 2y equal to x. If that is the case where 2y equal to x, and then I have constrained, then I have means this is what we have got, 2y equal to x. If I put in the constraint where x plus y less than equal to 3, but I have taken equal to 3 at the boundary. So if I keep, then I get 3y equal to 3, then y equal to 1, then x equal to 2. So when x is 2 and y is 1, we get a extreme point on the line x plus y less than equal to 3. Now I'll put there 2 to the power 2 by 3 into 1 to the power 1 by 3, means that will come as 2 to the power 2 by 3. Whatever it comes, there fxy that falls on the x plus y less than equal to 3, that is the value where f would be maximum. So this is called kind of constrained maxima or minimum. Okay, constrained maxima or constrained minima. If I want to calculate constrained maxima and minima where the function is fxy and constraint is gxy, then we have to calculate the gradient vector of fxy, gradient vector of gxy, considering that both are in same direction where they meet each other. Then I say gradient of fxy means fxi plus fyj equal to lambda braces gxi plus gxj. Now, based upon the lambda, I have to now, so fx equal to lambda gx, fy equal to lambda gy. So lambda equal to fx by gx and lambda equal to again fy by gy. Now I have to equate it, and then I have to find the kind of the value of x and y. Place it into gxy and find the value of x and y, set of value of x and y. Now, those sets are maxima and minima. Now set against fxy and see they are maxima or minima. So this is that way we calculate that on the line, on the boundary where dxy has boundary, on that boundary, what is maxima or minima where fxy passes it. Other is inside the boundary, what is maximum and minimum. For that we have to calculate dfx by dx, dfxy by dy partial derivative, set it to 0. If I set it to 0, then it becomes x equal to 0 and y equal to 0. If I do the derivative fx equal to 0 and fy equal to 0. If that satisfied x plus y less than equal to 3, at that point also we will see the fxy. So we have two extreme points. One is 0 comma 0 and another is 2 comma 1. Now at both points I'll see that fx attains maximum. So fx attains maximum when it is 2 comma 1, and that is the maximum. So first we try to do fx, fy, set it to 0 and find the minimum maxima and check if it is satisfying the constraint region. If it is satisfying, keep it. Then next go by Mr. Lagrange fundamental, that at 1f keep changing f contour, and at 1f it will be tangent to the constraint line or constraint algebraic equation. So that x0 y0 where it touching, it is tangent, the constraint is tangent to the fxy. There you calculate the gradient vectors, and then gradient vector are in same direction, so one will be lambda multiply of the other, and then find x and y, and then check against fxy that what are the value it is attaining. All the values now you check which one is maxima and which one is minima. Though no dual derivative works here much way. So this is how we kind of find the maxima or minima. Now, there are many questions here. What is the value of lambda? What is the value of lambda? So that we will see. And there is also Lagrange function that comes into the picture. Now we have fxy that is constrained over gxy. Now Mr. Lagrange, he went ahead and he saw that lambda is the guy which is doing all the nonsense. So he created another function called Lagrange function, that is where independent component is x, y and lambda. X, y and lambda. If for that he created another function that is not constrained over anything. If that is a function is not constrained over anything, then typically the way we find out maxima and minima derivative, all the partial derivative we calculate against x, y and lambda, and then we get the xy point. So Lagrange fundamental is that there is another function, unconstrained function. Leave the constraint gxy. fxy is a normal graph, gxy is a constraint. Now Lagrange, another function comes into the picture where independent variable is x, y and lambda. And then he came up with a function. He came up with a function. Okay, that function is fxy minus lambda gxy and something like this. So if there is a function called Lagrange function which is function over x, y and lambda, then keep calculating all the partial derivative. D Lagrange by dx, d Lagrange by dy, d Lagrange by d delta, and then you find the algebraic equation, set it to 0 all of them, and then try to find out x and y. Now set it against fxy and then see it is maxima or minima. So Lagrange function is a fixed function which is in term of fxy, gxy and c is a constant. Means if I have a kind of, there is c, if I have a constraint region x plus y less than equal to 3, 3 can be replaced with a constraint c. X plus y less than equal to constraint c. So though he mixed everything, lambda, constraint, fxy, gxy, and made a full-fledged function that is a function over xy and lambda. He called it Lagrange function. Now this function you don't have to, since it is a mixture of everything, now you don't have to worry about any constraint at all. And keep finding the partial derivatives and then equate to 0 and you get the x and y. But underneath you are dependent upon the constraint because gxy is there. Fx Lagrange function is nothing but fxy, gxy, lambda, c, everything is there. So gxy is there. So you are dependent upon the constraint. How you are not dependent on the constraint? You are mixing in a one, so altogether it is same. Not much difference, or there is no difference. Only thing you put in a combine all the effort what you made separately fxy and gxy and combine gradient of fxy equal to lambda gradient of gxy. He combined and made a Lagrange. That's okay. Then he proved also then what is lambda. If lambda has a value, lambda we can calculate now. Gradient of fxy equal to lambda gradient of gxy. Now we have xy point. Then at that point, what is this? Then we can calculate the lambda. But lambda he calculated also, and if I have a constraint c, then he saw that if I increase constraint c by 1, then how much f increases? If x plus y is less than equal to constraint c, we took example at x plus y less than equal to 3, x plus y less than equal to c. If I shift this constraint line to another line x plus y less than equal to c plus 1, if I make 1 unit change in c, constraint c, then how much the f would change? F has a maximum at x0, y0 when constraint is c. Now if constraint increased by 1, c plus 1, then x0, y0 would shift. For that, f would shift. So if constraint changes 1 unit change, then how much the function is changing? df by dc. If there is a constraint changing 1, then how much function is changing? That is lambda. So this is what he proved it. So that is lambda. Means proof is a kind of not Very difficult. If I say df by dc, then I can say df by dx into df by dx into dx by dc as per the chain rule. So df by dx into dx by dc plus df by dy into dy by dc as per the chain rule for the separate component of the x when partial derivative. Now df by dx is nothing but fx, partial derivative along x-axis. So df by dx is nothing but fx is nothing but lambda gx. So lambda gx into dx by dc. So lambda gx means dg by dx into dx by dc plus lambda dg by dx into dx by dc plus lambda dg by dy into del dx by dc. It is exactly what we started the discussion with the df by dc. Now, if I take lambda out, then inside the bracket we get dg by dx into dx by dc plus dg by dy and dy by dc. dy by dc. dg by dx into dx by dc plus dg by dy into dy by dc. Hold together what we see, then it is nothing but gxy. So dfx, that is dg by dc, dg by dx into dx by dc. Dx, if I cut chain rule, then it is dg by dc plus again dg by dc. So lambda dg by dc means df by dc equal to lambda dg by dc. Okay, so df by dc equal to lambda dg by dc. Okay, so through this, now dg by dc, so dg by dc is 1 with constraint 1 unit change in the constraint. How much gx is changing? So gx and constraint is same. If gx is x plus y less than equal to 3, then gx is constraint 1, that is c. So dg by dc is 1. So df by dc equal to lambda. So if I change the constraint by 1, then f would change by lambda. This is what Mr. Lagrange found. So this is nothing is natural. All terminology of the lambda and those things are by Mr. Lagrange. Nothing is required. What became as df by dc per unit change in the constraint brings how many unit of change in function is lambda. This is what we see, that is lambda into dg by dc, that is 1. So lambda. Okay, so we will have a disclosable item, or probably I'll try to find patent on this. So whatever we will see now next, that how we can find the kind of uh, extreme point as far as constrainment is concerned. So for constraint function gxy, how smoothly idea, if we do something that is not available anywhere, then it should be simple. We are not trying to find out something that is very complex, but we found it. Idea is whatever we are finding, okay, a new way, other way, that should be simpler to the existing one. Then only it will be called as that we found something. Otherwise, if you find something that is in 50 pages, but it is different, that doesn't make any sense. So we have also found a solution where fxy has maximum or minimum provided there is a constant function gxy. But method is absolutely different. So that we will see. I thought this would be the last session in the maxima-minima, but probably we will have one more. And that later we'll talk more when we will talk more on it. So that we will see.